Hi folks, and welcome back to educator.com. This lesson is going to be about Ohm's law and power. So our objectives are going to be to define and calculate resistance, current, and voltage using Ohm's law, and to calculate the power dissipated and energy used in electric circuits. This will be the basis of much more of our circuit analysis moving forward. So, Ohm's law. Ohm's law relates resistance, potential difference, and current flow. Can be written in several ways. V equals IR, where V is the potential drop across a circuit element, is equal to the current flow times the resistance. And you can look at it in a couple different ways, and you use it so much that sometimes I've used these circles to help me understand or to quickly derive exactly the version of the formula that I need. If I'm looking for V, what I would do is I would cover up on the circle the V. So if I cover up V, I find out that V is equal to I times R. In the middle, if I want to find current, I cover up the current. I, therefore, must equal V divided by R. And one more version, if I want to find resistance, I cover up resistance, and I find that R is equal to V divided by I. Just a quick little way to manipulate that formula that may save you some time. Now let's start by talking about resistance of a wire. The current in a wire is 24 amperes, so I equals 24 amps, when connected to a 1.5 volt battery. V equals 1.5 volts. Find the resistance of the wire. I'll use Ohm's law. R equals V over I, which is 1.5 volts over 24 amps, or 0.0625 ohms. Pretty straightforward. Let's take a look here at circuit current. In a simple electric circuit, a 24 ohm resistor, so now R equals 24 ohms, is connected across a 6 volt battery. V equals 6 volts. What is the current? I'll use another version of Ohm's law. I equals V over R, which is 6 volts over 24 ohms, or 0.25 amps, or 250 milliamps. How about a graphical problem? A constant potential difference is applied across a variable resistor held at constant temperature. Which graph best represents the relationship between the resistance of the variable resistor and the current through it? Well, R equals V over I, and we're holding V constant. So we've got R on the X and current on the Y. What's going to happen to R as I increase I, or what's going to happen to I could write it also as V over R. As R gets bigger, current must be getting smaller, right? So right away I can see that that must be answer 1. We've got an inverse relationship. As R gets bigger, current gets smaller. As R gets smaller, current gets bigger. So a little more on Ohm's law. Ohm's law isn't truly a law of physics. Not all materials obey this relationship, but it's a very useful empirical relationship or experimental relationship that holds up in many different circumstances. It's great for conductors and resistors, and an easy way to test if a material is ohmic is to plot the voltage versus current through it. If you get a straight line, the material is what we would call ohmic. And the slope of that line tells you the resistance of that ohmic material, the resistance of that resistor. So, the graph below represents the relationship between the potential difference V across a resistor and the current through the resistor. Through which interval does the resistor obey Ohm's law? Or through which region, which interval is it ohmic? Well, it's ohmic where this is a linear relationship. So that's going to be from B to C in this section right there. So BC is where it obeys Ohm's law. Electrical power. When current is flowing through a circuit, it causes a transfer of energy into different types. The rate at which electrical energy is transformed into other types of energy is the electrical power dissipated. In a light bulb, this corresponds electrical energy being transferred to light and heat, where typically the brightness of a bulb is related to its power output. Let's say is proportional to power output. In television, for example, electrical energy is converted to light, sound, and heat. Is 1,000 watts times 3,600 seconds, which is going to give us 3.6 times 10 to the 6th joules equals 1 kilowatt hour. So a unit conversion there for someday if you're trying to figure out what your electrical bill is corresponding to. So let's take an example of a toaster here. A 110 volt toaster, V equals 110 volts, draws a current of 6 amps, I equals 6 amps, on its highest setting as it converts electrical energy into thermal energy and hopefully gives you a nice, tasty, delicious breakfast or toast. What is the toaster's maximum power rating? Well, power equals I times V, where 6 amps times 110 volts, which is going to be 660 watts. Or how about an electric iron? We've got to go make our shirts nice and wrinkle-free. An electric iron operating at 120 volts, V equals 120 volts, draws 10 amperes of current. How much heat energy is delivered by the iron in 30 seconds? And if we're looking for heat energy, what we're looking for is either work or energy. So let's say we're looking for W. Well, if power is work divided by time, then work equals power times time. But power is V times I, so this is going to be V I T. Therefore, the heat energy is going to be the voltage, 120 volts, times the current, 10 amps, times our 30 seconds, or 3.6 times 10 to the 4th joules. How about the power dissipated by a resistor? A potential drop of 50 volts is measured across a 250 ohm resistor. So our resistance is 250 ohms. What is the power developed in the resistor? So we're looking for P. Well, this time I'm going to use power equals V squared over R. So that'll be 50 volts squared divided by 250 ohms, or 10 watts. Another version of our power formula. Let's try one more. What is the minimum information needed to determine the power dissipated in a resistor of unknown value? Remember, power equals current times voltage. So if we have just the potential difference across the resistor, just V, we don't have enough information. If we have just the current through the resistor, we're not going to do it. Current and potential difference, yeah, that'll do it. And current potential difference in time, no, we don't need time. That can't be the answer. Correct answer, current and potential difference only. All right, hopefully that gets you a great start on Ohm's Law. Thanks for watching educator.com and make it a great day.